Hello, welcome back to a new video in my D3D12Ez video series. In this video series, we're going to do an ad hoc approach onto DirectX 12, where we're going to basically just explain as we go how DirectX 12 works, how we all get this running, but still going to explain it so that you can understand it. Until now, it was kind of like detailed, but as deeper as we're going to dive into DirectX 12, it's getting more and more complicated, and I'm going to reduce myself more and more than actually like not telling you how everything works. But you're gonna always at least know the basics on how it works. Alright, so in the last video we have taken off by creating ourselves a device, a common queue, and a fence for synchronization between the device and the CPU, so the GPU and the CPU, or GPU-GPU synchronization. Just a bit of a general approach on how synchronization works in this case. Now what I want to do in today's video, I want to expand on that and talk a bit about also common queues, not common queues, command lists and command allocators, and how we're going to do the actual synchronization between these. And yeah, let's get directly started and let's talk about synchronization. Now, how does synchronization work between the CPU and the GPU? Now, in general, every work that we're gonna put on the GPU is gonna go through that single common queue. That makes many things easier because, of course, you can do, as I told you last video, make an approach of like one separate common queue for like copying work, one common queue for doing compute work, maybe even a common queue for doing video processing, maybe a common queue for rendering. And if you're overdoing that, you might end up with like having, especially if you're like loading videos, you're gonna end up with like 3, 4, 5 common queues that you all need to manage and maybe even need to synchronize between them. But in our case, we want to keep it simple and just have one queue, and thus also have a very, very simple synchronization mechanism between this queue and the other point on our application, which is in this case just the CPU. Because the only thing that we are really concerned about is our queue ready with the work that it shall do? And that's exactly what we want to do. Very simple. We just want to check the point, is the queue finished with its work? Now again, just as a revisit here, how does the queue work? Well, the queue basically works by calling a function on it that puts work on the queue, or putting kind of like an event on that queue. Now, what we need to do if we want to kind of like know if the queue is finished with a work, what we basically do is we're going to add another work on that queue. We're going to add a signal work. So basically we're going to tell the queue, hey, signal myself a fence with a certain value, and then what we can do is basically wait until the fence gets this value. And then we are 100% sure that any pending work that was previously on that queue has been finished and is flushed. So that's the idea. There might be work on the queue. We're gonna add another event on the queue, in this case a signal, and as soon as the signal is through that queue, so as soon as we kind of like see the fence taking the actual value that we have told the queue to set the fence to, then we know the work on the queue is finished. And that's basically what we want to implement. Not that hard. Now, what I want to do that is I'm going to write a void here, and I'm basically going to call that one signal and wait. Signal and wait is the function that we're going to write, and the idea of signal and wait is we're going to signal the queue and we're going to wait until the work is done. Now, how I'm going to implement that? Well, the implementation is very, very simple. We're going to take a look at our queue. We're going to call the signal function, which means signaling work. The signal function takes a fence and a value. The value that we're going to take is the fence value, and of course, this fence value needs to be modified. What I'm going to do is I'm going to do a pre-increment here, so it's going to be incremented and the new value is going to return. And the only thing that we are now concerned is that basically our fence here is basically bigger equal than the fence value, which obviously seems like it works because I can do pointer arithmetics, but that is not how it works. It's not that simple. We can't just tell the fence what it is. We actually need to ask the fence for its value. We can get the completed value of the fence, and as soon as this is bigger equal, everything is good. So basically we need to invert the logic. As long as it is smaller, we basically wait. So it's not an if, it is a while. That's kind of like the idea. While this is smaller, we just idle around and do nothing. What can we do while idling? There's a nice little switch to thread function in theory on the Win API that is basically going to tell Windows that our thread is currently not able to execute. Please let some other threads execute. However, this is not a good idea because what this concept is basically doing, it's polling. Our thread is the whole time, it's always waking up and it's always asking, hey, do I get my work? And at some point, Microsoft might even schedule our thread in a bad way. That can happen. because we are basically polling all the time. And if we are polling all the time, we are basically doing it in a bad way. We have an operating system available, and an operating system tries to schedule your application and the thread your application is running on as good as possible. And we can't do that if we are always polling. If we are always polling, we are basically saying, all right, our thread is not there doing work, do some other work. And what the operating system is basically doing, it's putting us into a queue way back in a queue slot. And as soon as we are first in that queue, we're gonna resume working. However, that's not the ideal way of doing that. What we want to do is we want to actually abuse the operating system a bit more. What we actually want to do is we basically want to tell the operating system, hey, put our thread to sleep until that work is finished. Because if it's that way, we can basically be directly waken up and put it into the front of the queue. If we configure our application in the correct way and fiddle a bit around with process and thread priorities, but the general idea is that's a bad approach. You don't want to do that. You are spamming the DirectX 12 API. You might have bad scheduling with the Win API. That's not something that we want to do. Bad approach, not what we want to do. What we want to do is we want to actually now create a event. What we want to do is create a Windows Win API event. The Win API event, it's basically just a synchronization mechanism between the operating system and your thread, or your threads between your own threads. It's in general just a thread synchronization mechanism. An event, a CPU-sided thread synchronization event. And it kind of like makes sense, right? The signal and the fence, it's a GPU-sided signaling and synchronization mechanism, which is basically doing it all on the GPU side. And now we need a CPU-sided signalization and a communication synchronization primitive to basically sync between the CPU, basically the driver and our application. So the driver at some point knows that the work is finished and can then wake up our thread and say, hey thread, now you are there to execute work. And that's what we want to do. We do this by, first of all, creating an event for that. Event is a handle in Windows. I'm going to call this one fence event. By default, the handle shall be null. And well, I think it's a pointer, right? The handle is a pointer. If I hover over that, it's a type def void pointer handle. So yeah, maybe just put this null pointer. All right, so event needs to be created. When do I want to create myself an event? Well, we'll create a fence. Maybe let's then create an event. So fence event equals create event. Very simple. Now, you can share events across multiple processes and synchronize between processes. Advanced stuff, we don't want to do this. Null pointer. Manual reset, no, we don't want to do that. The event shall automatically reset itself. Initial state is false. It should not be directly signaled. So let's put this to false. And then we need a name, since we are not synchronizing that. And between processes, we're just going to put it to null pointer, and everything is going to be okay. Now what I'm going to do is I'm returning basically fence event not equal null pointer, just to have this a bit checked in here. All right, so now we have a fence event, which of course needs to be cleaned up. So close handle, fence event done. Now, how do we work with that event? Well, basically it's very simple. We have now signaled that fence, and what we now need to do is we need to tell the fence that it should set a event on completion. So we tell the fence to set a event on completion. It shall tell this event as soon as it reaches this fence value, and then we basically provide the event here. And yeah, basically what I want to do, if this succeeded, then I want to wait for it. Else we could do an STD exit to basically go out of that. Something that I do not really like to do, but there are no other methods. We don't have exception and advanced stuff in here. So if that succeeded, everything is good. Else we're just going to STD exit, maybe with -99. Now let's just do -1. And -1 is always a good value. It's always something that just says it failed and not really gives information. And yeah, that's good. We like that. All right, so now we basically have told the fence to set that event as soon as it is completed. And yeah, that is basically the idea here. So the fence is going to be notifying the event when it gets the complete message from the GPU. So in general, in the background, the driver is going to set the fence, and then DirectX 12 is going to notify that an event is listening for that, and then DirectX is going to notify the event. Now, what we need to do is we just need to wait for the event. So wait for single object. It's called like that on Windows. those. Now we want to wait for my fence event, and then we can provide a kind of like timeout. I do like to put a timeout in here of 20 seconds. This is the maximum that it shall ever take. And what I want to quickly verify is that this is equal to wait object 0. If this is equal to wait object 0, everything is good. We can return, or what we could not do is we could check if it is not the wait object 0, and if it's not the wait object 0, do another std exit because something has gone wrong. The event basically timed out. It did not return within 20 seconds, and something has gone wrong, and the application will terminate then. That is the basic idea here. Now, wait for single object is an advanced function. It's basically going to tell the Windows operating system that the current thread is waiting for that event, and if another thread is going to set the event, our thread is basically directly wakened up. Might not be 100% directly, but it's at least like wakened up in a prioritized way, and dependent on that event, you could provide advanced values and tinker a bit around with that to make this even more performant. But yeah, normally in a proper engine, you would never use events and wait for single objects. You would do it differently, or you would use events, but you would check these events differently. You would not wait for the event, you would check the event. Use a timeout of 0 to basically check it. That's kind of like the idea on a proper engine, but don't want to go into too much details there. Okay, so now we have a way to synchronize with the GPU. That's kind of like the idea now. Now what we want to do is, now we want to be able to operate. Now how do we operate? Well, we're going to operate by having a comment list. Now a comment list is basically what accompanies the comment queue. The comment list is basically one of the things that can be executed on the queue. You can execute as many comments lists as you want on the queue simultaneously because, well, it's getting serialized by the queue for working on the GPU. But what you can do is on your CPU side, you can have as many comments lists as you like. The comment list itself is basically just a front end for recording work. There is, especially if you have the debug layer attached to it, probably some validation attached to a comment list. So the comment list is basically checking your parameters and then at some point emits work. Now a comment list itself is not really useful. The comment list is just a front end. What we need so that we actually can do the work is also a comment allocator. A comment allocator is a block of memory. And this block of memory is responsible for actually backing all of the commands that you are recording with the comment list with memory, because the commands at some point are transformed into kind of like a binary interface, a binary API that is then transformed to the driver, and the driver can then upload the actual list of comments to the GPU, and all of this stuff can be handled in the background, but we need some allocator that is basically backing up all the memory for that. And that's basically the idea. You need a comment allocator that's storing the memory for it. It's also important that the comment allocator is not going to be resetted or reused until the work has finished on the GPU, because I think it's also used as a context for the GPU to also back the memory on the GPU side. So there's advanced stuff going on in here. But what you need is a command allocator. Basically, it is just a memory allocator for your comments. Command allocator. And then what we need is a ID3D12 graphical comment list. ID3D12 graphics comment list, not a graphics comment list, probably up to 7, 8. Yeah, 7. Yeah, I correctly eyeballed it. My command list here. So we need to allocate the list. List is the front end. Recording comments to the allocator. If you are starting the work on the queue, you can reuse the comment list with a different allocator as long as the allocator stays alive until the work is done with the queue. So the comment list is something that you would kind of like have pooled somewhere. The allocators were also something that you would have pooled, and the allocators would kind of like transform its ownership between the execution unit of your engine and the pool and the front end. And the graphical comment list would be just basically free floating. You could take one, return one, take one, return one, as long as you're doing it in the right format. All right, so allocator and list. Now we have these, we need to create them. Where do we create them? Probably after the fence, right? Somewhere here. Now we've created the event here, so maybe I should check them. The if is gonna get a hell of a lot of different. No, I should have just basically returned false every time something failed, but there's nothing that it's too late to do. It's basically just the better idea in this case. So if this failed, I'm going to return false, and the default path is going to return true. This makes just our code a hell of a lot of more straightforward. It's going to violate every law that some of the people that tried to teach me software engineering failed to teach me. They said just one return statement per function. No, not in C++. Clean code makes your code slow, and we have writing engines, so that's probably the way that we want to go here, right? So yeah, return false. But of course with the failed one, then if not in fence event, return false. That's all good. False. There we go. And now what we can do is now we can create our comment queue and our no, not our comment queue, our comment list and allocator. So device, create comment allocator. Now for the comment allocator, we need to provide a comment list type. D3D12 comment list type direct is what we want to use, because our queue is also for direct comment lists. So our allocator should be able to hold them in our list later on as well. It's just as simple as that. The allocator is created like that. Comment allocator in here. It is just a matter of that call here. So very simple. If failed, that one, boom, boom, return false. As simple as that. Comment allocator created. The queue itself, the list itself, create comment list. It is also simple. Creating a comment list, there's also a create comment list 1. And I think comment, what is the difference between one? Node mask, type. What you're taking, node mask, type. Yeah, we use the one that's taking less parameters. Node mask, I told you, always put them at 0 and they're gonna be good. And you're gonna use the right GPU in your SLI stuff. And then we need to type. We need some flags. I think there aren't even any flags. Are there flags? Flag? No. My IntelliSense is broken the whole day, but there are no flags. Now another IID PPV args to my command list here, and we are good. Right, creating these two is most trivial thing that you're gonna do when you're DirectX 12 live, because they really don't do much things. The one is a front end and the one is a memory allocator. Very simple. I mean, there's no custom allocator, of course, because it might need to allocate to the GPU as well. But basically the idea is just, you're just gonna have the overhead of creating them, and then you need a way to manage them on your own. And if you're managing them correctly, you can reuse them and you have them pooled and you can go nuts, but we're not going to go nuts in here. But that's the whole point, right? Simple, created, finished. Of course, if we create them, we need to clear them. Command list release. Command allocator release. And that's it. Now we have it all rolled back correctly, and now we can start using the comment list. How do we use the comment list? Well, we use the graphical comment list by providing a function to use it. I basically want to have a function void, not a void function. I want to have actually, since I don't really need this as a com pointer, since a comment list is not really meant to transfer its ownership or to be actually referenced somewhere else. I'm going to use a raw pointer here. The comment list is more like used as an instance. You get the comment list from the context, you use it, and then you say dispatch, but it's not really something that needs to be memory managed. It's something that's passed around, but we do not need any of my com pointer management stuff in here, so we're just going to provide a pointer here, normal pointer. By the way, there are also non-graphical comment lists. There's, I think, a ID3D12 compute, ID3D12 command list. I don't know why it's a bit bad today, but there's like a debug comment list, graphic comment list. There might be even a compute comment list. I'm not quite sure if it's called compute comment list, maybe not. Meta comment, I don't know. However, there are multiple comment lists. I think like the normal comment list can do compute work, but not quite sure if that. However, it doesn't need to be a graphics comment list. I think if you're including D3D12 video, then you also have a video comment list, and yeah, you get the point, right? There are multiple specialization of the thing. Right, get command list. So maybe let's call this one init command list, because we are doing some initialization. Init command list, that's more of what we are doing. We are initializing the command list and we are returning it so that we can work with it. So how do we initialize a command list? Well, the first thing that we need to do is we need to prepare our comment allocator. Now, basically, we're calling the reset method because we want to reset our comment allocator so that it is ready to record new comments. Then we do the same thing for our comment list. We are resetting our comment list. We are resetting it and providing a new allocator where it shall record its data to. And then we can provide an initial pipeline state. This is optional. We just provide null pointer. We haven't talked about that. And then we're just going to plainly return our comment list as a pointer. And everything is good. We have the comment list ready to execute work on. Now, the next thing that we need to do is we need to have the other way around. We can need to initialize it, and then we need a way to start the work. I'm going to call this one dispatch command list. So we have an init and a dispatch function. We do not need any arguments because we just have one. So we have a dispatch function. How do we dispatch them? Well, I'm going to ask my queue to execute comment lists. We need to tell it how many comment lists we want to execute. We want to do one because we just have one. And then we need an array of comment lists that we want to execute. Now this is a bit special, but it's not that hard. D3D12 comment list pointer lists. And then we have the array stuff, and then we're just going to put in our one and only comment list, and then we can provide the lists in here, and we have them available to execute on the GPU. Now this avoid function doesn't really do some checkings, and we are done. Now this is all still our asynchronous concept. We have now pushed that on the command queue, and now it is executing. And what I also want to do is I want to wait for it, of course. So I'm going to call wait. How did I call the function? Signal and wait. Okay, so we want to call signal and wait here so that we also signal the command queue and wait until the work is done. That is kind of like the idea that we are doing. And by doing it like I have done it now with the init command list and the dispatch command list, we basically have taken the asynchronous API of DirectX 12 and transformed it into a nice and friendly blocking synchronous API for our learning purpose, so that we are not need to be concerned about all of the asynchronous stuff. That's everything we need. Now we have it ready to execute and ready to work. Now the only thing that we need to do is we need to provide ourselves a while true loop, because basically while we are doing rendering, we're doing something on a per frame base. So we need kind of a while. And then, well, auto command list equals dx context get init command list, and we are ready to work. And somewhere down here, dx context get dispatch command list. I mean, dispatch is kind of like misleading because it kind of like leads to that we also have kind of like a wait for. So yeah, maybe let's maybe call this one execute here as well. We have Visual Assist, so that's not that big of a deal to rename functions. I mean, still Visual Studio is gonna freak out if we do it, but yeah. Okay, but that's everything that we need. Now we have a comment list that gets executed with no work, and DirectX might probably yell at us and tell us, hey, don't do stuff on it. Right there, you're gonna see it. DirectX is hardly yelling. Let's maybe continue and stop the application. DirectX is yeah. Okay, no, this is actually something different that we are doing. I forgot the thing that I always forget. A comment list needs to be closed before it can be executed, basically. A comment list, you need to call a close function. That's a void function. You need to close a comment list before you execute it. And maybe this is something that we could check. Right? No, we don't need to check it, right? We're just gonna close it and it's good. This, if there's something invalid on the comment list, so if this, maybe we wanna wrap this in a if succeeded, and only if it succeeded we wanna execute and wait then. But yeah, this is because basically this is the debug layer. This is the debug layer yelling at us. The comment allocator cannot be reset because the comment list is currently being recorded with the allocator. Reset fails because the comment list was not closed. And this is basically thrown a hell of a lot of times because we have a while loop. This might get rid of it, but now we might probably get a warning that a comment list, no, we can execute a comment list without any comments on it. That's interesting that the debugging layer is not complaining about us. By the way, we are using quite some memory, 72 megabytes of memory, because we have loaded some big ass libraries on top of us. I mean, release might consume less, but you see DirectX 12 is memory hungry. On release, yeah, 10 MB less, but this is DirectX 12. Eating away memory just because it's there. That's the point, right? Now, I don't know what it is doing in the background. I mean, there are a bunch of stuff that is loaded like the NVIDIA driver, and probably they are already allocating some staging buffers for comment lists and for the comment queues. This is why this is basically taking away so much memory. But yeah, that's not really memory efficient, right? But that's not the point of the video series. You understand how DirectX 12 works. But that's a kind of the construct that we have. A while true loop. And we are executing, initializing, executing, but we are not doing any work. But we could. Now we actually are on a way that we could call a draw function, but we are not there, right? This means the draw function is so close, but it is so far. So thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.